Swayam Prabha. Digital India. Educated India.
Hello and welcome to the discussion sessions of production technology theory and practice. So, let me remind you that in our last session we started discussing the economics of machining, because we said that our aim or the aim of the production is to make a part of particular shape, size, finish and accuracy with minimum cost. Okay. So, to have the minimum cost, we have to look into the different aspects, particularly the cutting parameters. Okay. For us, it is more important and convenient to see how the cutting parameters will have the effect on the cost. Okay. So, then it has been found out also from the Taylor's tool life equation that the since the tool life is affected by all three parameters, cutting speed, feed and the depth of cut, and there is an optimum value of the cost, and this is a compromise between the cutting speed and the tool life, because as you are increasing the cutting speed, although the machining time decreases and the production rate is increasing, cost is decreasing, but the tool life is becoming less. Okay. So, tool cost will be more. So, therefore, there is a relationship between or compromise between the cutting speed and the tool life, so that the cost could be minimum. So, therefore, we can conclude that on the minimum cost there will be effect of cutting speed, feed and the depth of cut. Okay. So, what we said here is that we are assuming that we are turning a cylindrical bar of capital A, here it is capital L, because after that we have used the capital L for the length. This is the diameter of the cylinder and we are turning this. Okay. So, we have the important cutting parameters as cutting speed, feed and the depth of cut. Technological aspects, we said that these are the surface finish, power, force, and the economical aspects are minimum production cost criteria, maximum production rate criteria and the maximum profit rate criteria. So, what I said and what I discussed with you is that each of these criteria, that is either it is a minimum cost criteria or it is a maximum production rate criteria or it is a maximum profit criteria, you will have a certain optimum parameter on cutting speed, optimum cutting feed and the optimum depth of cut. Okay. So, but these parameters, these optimum parameters may not satisfy the maximum production rate or maximum profit rate, all right, and vice versa. That is, the optimum value of the cutting speed, feed and depth of cut for the maximum production rate may not satisfy the criteria for the minimum cost or maximum profit rate and so on. So, then we said that the overall cost per piece consists of the raw material cost, okay, plus settling and ideal time cost, plus the machining time cost per piece, then the tool changing time cost per piece and the tool cost per piece. Okay. These are the 5 basic costs which are involved in the overall cost per piece, that is a final product. In here the material cost R1 and the idle time setup and idle time cost per piece cost, they are not actually dependent on the cutting parameters like speed, feed or depth of cut. Okay. So, they remain independent of the cutting parameters, all right. Now, the setup and idle time cost, this R2, this is equal to the time taken for the setup and we said that this is the settling and idle time cost per piece is Ts, that is multiplied by the payment that you are making for this time, okay, and that we said as the lambda 1, which is overhead plus the labor cost per minute. Okay. So, overhead I explained that overhead is everything else rather than labor cost, which is the building, okay, the facilities like the electricity, water, okay, hydraulics, then the pneumatic, then the chip removal, okay, carrying out of the chip, carrying out of the cutting fluid, wasted cutting fluid, and so on. Then we said the lambda 2 is the tool cost per grinding. This is used later. So, after the setup and idle time cost is determined, we will find out the machining cost, and this has already been discussed in our last session. We said that this is equal to the machining time that is incurred, and that for that we are paying the overhead and the labor cost. Okay. So, now T m we earlier found out is the length divided by f into n, and we are assuming that this is for one pass, because this was into multiplied by the number of passes. So, if the number of passes is 1, the machining time can be expressed by the L and the f n ratio. So, this can be n can be found out as V c divided by pi d, okay, and that can be multiplied by 1000, because it is the RPM to second, because these are the millimeter per millimeter per minute. So, that we are using as the second. Okay. So, T m we found out in second is pi d L by f into 1000 V. All right. Now, here of course, as I said that this is the n, which is the RPM, okay, rotational frequency. This is the diameter, this is the capital L is the length, that is why pi d L is the velocity, okay, cutting velocity, and therefore, the machining cost will be this multiplied by lambda 1. This is lambda 1 pi d L by 1000 into V into F. Okay. Next is the tool changing cost. Tool changing cost is R 4. R 4 will be determined by how many times we have changed the tool into that time taken for changing the tool, each time you are changing the tool, okay, and that multiplied by the overhead and the labor cost. So, T m by T is the frequency of tool changing into time that is taken for changing the tool. T c t is the, we said T c t is the tool changing time somewhere. T c t is the tool changing time. By the way, it is not the capital T, it is the small t, all right. T c t is the tool changing time, all right. Now, this multiplied by the frequency into the overhead and the labor will give you the tool changing cost. Now, here this T is the tool life. Okay. From the Taylor's tool life equation, we can say that V t to the power n is equal to C constant. Okay. Let us say this is equal to C constant, and constant can be said as k to the power n. This is also constant, k is constant, n is constant. Okay. So, C, this constant can be expressed by this k to the power n, where both this k and this n is this n, which is constant, all right. So, therefore, T is equal to k divided by V to the power 1 by n from here, if it is V to the power n, V t n to the power n is equal to k to the power n. So, if we put the T is equal to k by V to the power 1 by n, the R 4 will be expressed like this, that is the lambda 1 and the T m, we know that T m we have already found out, T m is equal to this, all right, because this we found out as equal to T m, machining time, and that machining time we are using actually here. This is the T m into this 1 by T into T c t into lambda 1. So, this will be the R 4. R 4 is the tool changing cost. Okay. Now, next is the tool cost per piece, that is the R5, and the R5 again we have to find out that how many times we have changed the tool or the frequency of the tool changing. This is Tm divided by T, as we have said here, this is the frequency of tool changing. Alright, that we are multiplying by the lambda 2, and the lambda 2 is the tool cost per grinding. Okay. Now, what we are saying is that the person who is doing that, we are not paying the overhead and the labor cost in this case, because this is the part of that, okay, tool cost. So, overall part of the process. So, when the tool and another person is doing that, another, let us assume that another operator is actually giving the tool and you are changing that. Okay. So, you are changing these many times, and for each time you are paying the lambda 2. So, Tm by T is the frequency of tool changing, for that you are paying the tool cost, okay, and lambda 2 is tool cost per grinding. So, each time it is being ground, it is ground by somebody. So, the operator who is here, he is passing on to another operator who will be grinding. For that he is our operator is not being paid. So, therefore, lambda 1 is not considered here for this part, this piece. Okay. Now, this R5 therefore will be equal to Tm by T, we can easily find out, because Tm by T we have already done it here. Tm by T will be the entire thing, alright, pi dl by 1000 Vf into V to the power 1 by n by k, that is what we are writing. So, this is Tm by T, capital T, which is tool life, into the lambda 2. Okay. Lambda 2 is the tool tool cost per grinding. Now, the variable at our disposal is V only, that is the cutting velocity. Okay. We are not considering the cutting speed, feed and the depth of cut, and as I said that those also can be considered, but in that case the with respect to F we have to take. Now, here we are taking that this is, let us say, this equation or the R cost per piece, this is only dependent on the cutting velocity, we are considering that only, okay, because we are trying to find out the optimum cutting velocity for the minimum cost. So, here is the cost, and this we will consider, and this equation is dependent or a function of the cutting velocity only. So, F into this cutting velocity, okay, this is a function of velocity, is equal to the all 5 of them, R1, R2, R3, R4 and R5. Okay. So, separately we found out R1, R2, R3, R4, R5 and so on, we are summing them up. Okay. So, this we are making, since we have taken it with respect to V. So, we are separating out that V will be V to the power minus 1, here will be V to the power 1 minus n minus 1, and here also will be the same. Okay. Then what we are saying is that this V cutting speed will be optimum cutting speed if we take the first derivative of this equation and make it equal to 0. Okay. We will take the partial derivative of this equation and we will make it 0 to get the minimum or maximum. So, here we are saying that this is the optimum velocity. So, this is the maximum velocity that we can actually operate at, so that the cost is minimum. Okay. Now, therefore, we are taking the first derivative, partial derivative and making that equal to 0. So, if you take the first derivative of this equation, then these two are cancelled, because they are not dependent on the cutting velocity. This is the R1 raw material, this is the settling and the idle time cost. Okay. These are not coming into picture. So, these 3 are coming into picture, and this will be minus lambda 1 pi dl by 1000 V 1000 F to the power V to the power minus 2 after getting the derivation and so on. So, you take the derivation like this, then we are making that equal to 0. Okay. So, from here we actually take this common for all, you can see that pi dl by 1000 F and here V to the power V optimum to the power minus 2. Now, what we are saying is, as soon as we are making it equal to 0, this first derivative, okay, this V will be V optimum. This cutting velocity will be optimum cutting velocity, because we are taking the first derivative and making it equal to 0. So, therefore, everywhere we are putting that optimum here. Now, from in this equation we can actually take this common from everywhere, and here it will be only minus lambda 1, because we have taken this as common, and then here it will be TCT remaining, K is remaining, okay, and 1 by n minus 1 remaining V optimum to the power minus 2 we have taken out. So, it will be 1 by n. Similarly, here also it will be the same, except that this will be lambda 2. Okay. This has been taken out, 1 by n minus 2 has been taken out. So, it is 1 by n, and this is equal to 0. All right. So, V optimum, from here you can segregate the V optimum, and you will find out that V optimum is equal to k n lambda 1 divided by 1 minus n into lambda 1 TCT plus lambda 2. Okay. So, this is the minimum cost criteria for which the V is optimum, that is the cutting speed is optimum. Okay. Now, if we draw the curve of the cutting speed here in the x axis and the cost along the y axis, what you will find out is that this cost, total cost profile, will consist of 5 costs, right. That is, one is the raw material cost, second is the idle time and the settling time cost, third is the machining cost per piece, fourth is the tool changing cost per piece and the tool cost per piece. So, all those we can plot together to find out the total cost profile. So, that is what it has been done here. Now, this is the cutting speed. So, with respect to cutting speed, the material cost is constant, all right, it does not depend on the cutting speed. Similarly, settling and idle time cost will be also constant. This is IDLE, idle. This will also be constant, this will not change with the change in the cutting speed, as I said earlier. Now, the machining cost R3, let us see, R3 we found out like that. Okay. So, this is V to the power minus 1. So, it is a non-linear curve, all right, because R3 will be lambda 1 pi d L by 1000 F and V to the power minus 1. Okay. So, this is therefore will be a curve which is non-linearly changing with the increase in the cutting speed, and this is decreasing. As the cutting speed is increasing, the machining cost will actually decrease, okay, as you can see here. Now, similarly, the R4, tool changing time, R4 we found out as this. Here also we have the V to the power 1 minus n 1 by n minus 1, which is R4. So, this is also a non-linear equation, and therefore, this curve goes, if you analyze that, this curve will go like this, all right. This is the tool changing time cost, okay. And the R5 we have taken also V to the power 1 by n minus 1. So, this is the tool cost. So, here in this, total tool cost profile will be like this, which is actually summing of the tool cost, tool changing cost, machining cost, settling and idle time cost and the material cost, raw material cost. Okay. Now, if we look at this total cost profile, mind it, this is the total cost profile. Of course, this will be summing up. So, the curve can be somewhere, I do not know where, I mean we have not maintained the scale here, but this is only the profile. Okay. Now, in this profile you can see that there is a minima, okay, meaning that if we take this point, at this point the cost will be the minimum, let us say here. Okay. This is the cost which is minimum cost, and therefore, this will be the optimum velocity, and that optimum velocity, for that optimum velocity the cost will be minimum. Okay. So, this is the idea of this analysis, that we can find out the optimum cost. At this optimum cost, the tool will not be wearing out that much, so that the cost will be excessive and the time taken will be optimum, okay, so that the cost of the product would be minimum. So, overall if we operate at this cutting velocity, the cost will always be minimum, and if we take the cutting velocity less than that or more than that, in both cases the cost will be more. Okay. Now, next is the let us say maximum production rate criteria. What will be the optimum value of the cutting speed for which we will be getting the maximum production rate? Let us say the total time to make a product is T per piece, small t. The maximum production rate can be achieved if the total time required per piece is reduced to minimum. This is understood, that when the time is minimum, the production rate is higher. Okay. Rate is 1 by time, all right. Production rate is 1 by production time. T is the this time, total time, it consists of the settling 3 times, 3 different times, that is settling and idle time per piece, machining time per piece, and the tool changing time per piece, meaning that while we are machining one part, okay, we spend time in these 3, okay, in these 3 activities, that is we are settling and some idle time for each piece. For machining the part we need some time, so that is the machining time per piece, and the tool changing time per piece, that means how many times you are changing the tool and for each time how much you are paying, as I have shown it. But overall this is the tool changing time, how much we are spending time. This we are expressing as Ts is the settling and idle time per piece, Tm is the machining time per piece, and the tool changing time is the Tct into the frequency of tool changing, that is how many times we are changing the tool, that I have shown it to you earlier. This is Tm by T, and that value becomes this, that is pi dl by 1000 Vf into V to the power 1 by n by k. So, this is small Tm machining time divided by tool life, okay. That multiplied by the Tct, tool changing time, is the tool changing time per piece, okay, because mind it, Tct is the tool changing time we said, and per piece will be multiplied by this frequency of tool changing. Tm we have already calculated, all right. Tm we have calculated here, okay, and here we have calculated Tm, right. So, this Tm we can put it here divided by capital T. So, that also this we have seen, this Tm is here. So, this is the equation for the total time per piece equal to this. Now, for optimum speed, okay, we like in case of minimum cost, all right, this first derivative is equal to 0 with respect to V optimum. So, when the V is the optimum velocity. If we take the first derivative of this equation with respect to V, okay, we are segregating the V as the V optimum, because as soon as it is made equal to 0, the V will be V optimum. And like we have done in the earlier case, we find out the V optimum value segregating this V optimum, and you can see that if you simplify this, the whole thing will be common, it is getting into this is 0. Then the V optimum will be equal to k n divided by 1 minus n into Tct to the power small n. So, small n and the k, these are the constants, okay. These constants are the tool life equation constants, Taylor's tool life equation constants. So, once again I will come back, this n and the c is the material dependent, n and the k in this case, okay, because k to the power n, small n is the c. Now, n and c or n and k in this case, these are the material dependent, meaning that this the value depends on the combination of the tool and the workpiece material, and depending on the tool and the workpiece material, these values will be given in the handbook, okay. So, you can find out these values, and depending on the TCT, you can say that this will be the value of your optimum velocity. Now, next we can similarly find out that what is the maximum profit rate criteria. Okay. Profit rate P is given by S minus R divided by T. Okay. T is the total time per piece. Okay. S is the amount received per piece, excluding the material cost and the cost per piece, meaning that after selling, how much you are actually getting, how much you are selling it for. In one word, it is a selling cost. Okay. R is the cost per piece. Cost per piece we have already found out. This is the cost per piece. Okay. Then if we actually take the first derivative of this, S is constant, all right, and find out the value of the R, which is equal to R1 plus R2 plus R3 plus R4 plus R5, okay, divided by small t value is this. So, you take the ratio of the R by T, S being constant, then P you take as the function of the velocity and take the first derivative of this equation with respect to the V optimum and make it equal to 0, you will find out the value of the V optimum. Okay. So, here that V optimum value can be found out for maximum profit rate. Okay. Maximum profit rate. Now, here one thing I will again repeat, that in okay, here we are saying that in order to simplify the analysis, the cutting condition is generally optimized without considering any increase in the income here per piece. So, this selling price we are saying as a constant, as I said. Okay. Now, that I have already repeated, once again I will repeat that this V optimum value will not give you the maximum production rate or minimum production cost, okay, or this value of the optimum velocity for which you are getting the minimum production cost will not give you the maximum production rate or maximum profit rate, meaning that each one is unique for that particular criteria. Depending on which criteria you have selected, you have to decide that what you want to go for. You want to go for the minimum cost or maximum production rate or maximum profit. So, depending on that, you have to use that particular value of the optimum cutting speed in this particular case, so that that particular criteria is satisfied. And once again I am telling you that here it is for the simplification of the analysis, we have taken only the cutting speed. For example, in this case, let us say minimum production cost criteria, we have we could have kept this F, okay, and V is constant in that case. So, instead of V optimum, in that case it would have been F optimum, okay, and find out what is the value of the F optimum, right. So, similarly, we bring into this process, into this equation, the depth of cut, and then we can similarly make that equation and find out finally what is the D optimum value, and you will see that all these values can be found out, but for the time constraint we are not discussing all these because that will take a lot of time, but you can find out. This is a very similar operation that you will be doing, as I said, okay. Bring in the value of the here F is there, but you can also bring in the value of the depth of cut, all right, and with respect to depth of cut, then you take the first derivative equal to 0, and then it will be the D optimum or F optimum if it is with respect to feed, and so on. I hope this is clear. Okay. Now, although we got these optimum values, okay, that is the feed, speed and depth of cut, we have some restrictions, and we cannot always use these values exactly. Okay. Let us see these restrictions. The final choice of the optimum value of cutting speed that we have determined will have to satisfy a number of restrictions. These are the maximum power restriction or force and vibration restriction, speed restriction or surface finish restriction. I will quickly go through that, it is a common sense. For example, if it is the maximum power restriction, the maximum power can be found out by this equation. Okay. This is the empirical relationship of the power that is given by the constant Bw, okay, cutting speed, then the feed to the power m1 which is constant, and depth of cut to the power m2 which is constant. Okay. So, experimentally you can find out the values of the m1, m2 and Bw, all right, and you can set a, let us say you can find out the the variation of the Pw with the velocity, for example. So, overall we can say that Pw, that is the power, this is constant. Let us say if we take these as constant, that f is not changing, d is not changing, we will take only the cutting speed, then it will be constant Bw prime, okay, where Bw prime is Bw f to the power m1 d to the power m2 which is constant, let us say, because only v is variable. Then this equation m1 and m2 constant for given tool work combination. Okay. The maximum power available in the machine is limited by the power capacity of the main drive. When you are selecting the main drive, that is the motor, that has a particular power, and the power required for the cutting process cannot be more than the power available from that machine, otherwise it will stall, it will not work. All right. So, this velocity that you have got as an optimum velocity for the minimum cost or maximum production rate or maximum profit rate, that cannot exceed the power which we have for the main drive. So, if the V optimum is such that the available power is exceeded, the speed must be adjusted to meet this restriction. Okay. Now, speed has to be lowered, okay, so that we can match it to the main drive or prime mover, okay, which we have selected. That is the point. Next is the speed restriction. Now, most machine tools have the cutting speed in steps over a range, you know that like for example, if we have the diameter here, okay, diameter, and this is the, let us say, speed, okay, Vc we said. So, this is the maximum and this is the minimum, we have restriction this Vc minimum and this is V maximum, cutting speed Vc. So, now the the N, that is the RPM of the spindle, cannot be more than the V maximum. Okay. Diameter like Vc is the pi, d and the n. So, you give the value of the n, change the value of the n in such a way given the diameter that it is not crossing Vc maximum and it does not go beyond Vc minimum. Okay. Because you understand that if it goes beyond this, so our power will be exceeding, and if it crosses less than Vc minimum, then it will be a restriction from the built up edge formation, then it will come to the built up edge formation. So, suppose you have the N1 working here with the N1 some RPM, and at that RPM you have that D1. Okay. So, you are going along this and you cannot cross beyond that, okay, because it will be crossing then with this D1, then it will be crossing the power, okay, velocity. Now, you have to come back along this line, and from here you just take the perpendicular to this line and you join this line. So, then this will be N2. Again you are going from along this line up to this point, you cannot cross this, okay. Then you come back here, and from here you took the perpendicular and then you join this line, okay. So, this will be N3. These are the steps that we are talking about, that this is the step in the cutting speeds in steps, that means N1, N2, N3. And if you go through this curve, so this is the curve, this is actually called the saw diagram, because this looks like a saw, okay, how the steps are changing. So, these steps have, as you know, that they can be in geometric progression, okay, so that the whole headstock could be compact, that is, a gearbox can be compact. All right. Now, step closest to the optimum value should be used. Whatever optimum value that you have found out, that should match the step available. If not, then you come back to the next step, okay, with the closest V, and then V has to be adjusted. The V optimum that you have calculated from the minimum cost or maximum production rate, in that case that has to be adjusted accordingly. That is the point you are saying, that lower limit of the speed is generally limited by the formation of the built up edge. That is what I said already. Now, the force and vibration restriction, the machine components are designed for a maximum permissible load, okay, beyond which of course, the tool work deflection will be excessive, and that will result the dimensional inaccuracy, meaning the diameter will be defective or the length will be defective, okay, I mean the deflection and so on. So, therefore, the cutting speed can be expressed in this way. It depends on the feed and the depth of cut, okay. It velocity does not have much effect on that actually, cutting speed, okay. So, therefore, if we say that B p is constant, then it will be depending on the f to the power m 1 d to the power m 2, again these are the constants depending on the, all right. So, cutting speed has a very little effect on the cutting force, as I said. There is no restriction on the cutting speed in terms of cutting force, but this will limit the maximum value of feed and depth of cut that can be used here. Feed and the depth of cut, they will be they will affect the cutting force. Excessive vibration and chatter also put restriction on the cutting conditions. So, meaning that whatever V m you have selected or the optimum value you have selected, on that may not have much effect on the F c, but in that case the F and the D, which you could have also done, as I said that we have not done that in this case, but we could have also done the F optimum and D optimum, then these conditions have to be looked into and these values have to be looked into, and if it is not satisfying this equation, then they have to be adjusted. That is what it is said here. Now, the surface finish restriction, surface finish during the cutting operation that depend on the tool work material, tool geometry, cutting condition and the coolant. These are the 4 factors basically on which will affect the surface finish. Now, the surface finish restriction can be expressed as this, that it has more effect from the feed and the velocity. So, here the Bs A1 and A2, these are constants, and therefore, whatever V optimum that you have selected, it has to satisfy this equation. If not, then the V optimum that you have already calculated for the optimum for the maximum profit rate or maximum production rate or minimum cost, that has to be adjusted. Okay, this is what it has been said. This is what I wanted to discuss in the economics. Now, from the point of view of surface finish, feed marks are the predominant phenomena, and this puts a serious restriction on the feed, because feed has to be regulated so that feed marks are not do not remain on the machined surface. Cutting speed affects the surface finish, okay, by the formation of the built up edge, which gets smaller and disappears at sufficiently high speed when the temperature goes beyond the temperature of recrystallization, and then the surface finish improves. Okay. So, these are the 2 points which are important here. Well, our next topic is, quickly I will go through the thermal aspects of machining, where I would like to show you particularly, I have already told you initially that how the temperature occurs, where the temperature occurs, and how the temperature, this temperature is dispersed, okay, or dispersed, rather distributed. When the cutting process happens, that is the plastic deformation occurs, and the chip is formed from the shear zone. Okay. Here the material is completely plastic, and then it will actually the plastic deformation takes place here in the shear zone, and the chip moves over the rake face of the tool. So, because of the plastic deformation, a lot of heat is produced, and in this shear zone almost 80 to 85% heat is produced because of the deformation, plastic deformation. So, you should understand that plastic deformation is the basic factor why the temperature occurs. Next, this heated chip will flow over the surface of the rake face. Okay. So, during the flow of the chip over the rake face, there is a friction between the chip and the rake face of the tool, due to which 15 to 20% of the heat is produced actually. Okay. and about 1 to 3% heat is produced because of the rubbing between the flank face of the tool and the already machined surface. Okay. This is what it is said here. Now, the distribution occurs almost in the similar way as they are produced, that the heat is carried away by the chips. This is majority of the heat carried away by the chips. Okay. Then the heat carried by the tool, this is about 15% and less than about 5%, or carried away by the work here is here in this. So, this is about up to 5%, and this carried by tool will be here. So, this is about 15 to 20% produced, and the carried away also by the chip is majority. Okay. So, majority of the heat is carried away by the chip, followed by heat conduction in the tool and the workpiece. And remind you that the temperature changes with the cutting velocity in this way. So, as the cutting velocity increases, temperature will change in this way, and this is the distribution or the disbursement of the heat to the chip, to the tool and to the workpiece. Okay. Now, let us talk about the surface finish. What is surface finish? So, there are undulations on the surfaces. Okay. That is what we said, that these are the surface roughness. All right. And if you look at any surface which is machined under the microscope, you will see that there are surface undulation. It cannot be absolutely smooth. So, the surface finish is defined by the height of those spikes, how big those spikes are, okay, how big is the surface roughness. So, roughness in the produced surface is caused because of two reasons. Okay. One reason is the inherent geometrical configuration involved in the process, that is the ideal roughness. Inherent geometrical configuration means that we already have the tool with a certain angle, we will have a certain the condition of the parameter, we have a certain machine on which we are working, that will have certain accuracy. So, these are the inherent properties, they cannot be changed. Okay. Now, second is due to the built up edge, vibration, etc. So, the first causes which we cannot change is the ideal roughness, and the second cause, that is because of the built up edge, vibration, etc., they are caused the natural roughness. So, total roughness is the ideal roughness plus natural roughness. Okay. Now, the ideal roughness, as I said, that on this ideal roughness we do not have much control, because they are inherent, they will happen. So, ideal roughness indicates the best possible finish that can be obtained by a given operation. We cannot have any control on them. All right. Therefore, surface roughness in turning operation, when we are determining, let us say this is the exaggerated form, this is the depth of cut from here to here, okay, and this is the undulation, this is the surface roughness. So, surface roughness will be determined from peak to valley, distance between this point and this point, this will be given by, let us say, H max. So, this is the movement of the tool in one revolution of the workpiece from this point to this point, let us say. So, this is the value, as I said earlier also, that this is the value of the feed. This is millimeter per minute, millimeter of the tool movement, okay, per one revolution per minute of the workpiece. So, now if we see this triangle, let us say this is A, this is B and this is O, this is O. Okay. So, this is the triangle A, O, B, A, O and B, this is the feed. Okay. From this point, if we put a normal, let us say this is N. So, in that case the feed is equal to this distance plus this distance, all right. This distance is equal to, this is what? This is the H, right, from peak to valley. You can see that this is the H or H maximum here it is said. So, here we are taking as an H, same thing, let us say it is H, and therefore, this h is equal to or the h of the tan of gamma s, which is equal to this, and h and the cot of gamma e, this is the end cutting edge angle, this is the side cutting edge angle, this is equal to O n, let us say n. B n is this is equal to B n, okay, and this is equal to N O. So, B n plus N O is F, B n is given by this is the h and the tan of this, and N O is given by h and the cot of gamma I, because tan I will be opposite to that, all right. So, therefore, h common and the h is equal to h, that is what we have to find out, this is the surface roughness, okay. This is the h. So, h will be equal to f divided by tan of gamma s plus cot of gamma e, okay. So, this will be the formula that will tell us that on which the surface roughness or surface finish will depend, and in this case, that is the turning with the sharp tool, we can see that it depends on the feed basically, because for a certain tool our side cutting and the end cutting edge angle will be constant, and the h is directly proportional to the f. So, when we are changing the feed, our this thing is changing, surface finish is changing, okay. As we are increasing, this h is increasing, surface finish is deteriorating, that is the conclusion. Now, if we round off this tool, instead of having this sharp edge, if we are rounding off, in that case you can see the picture in this way, okay. It is not sharp, but with a nose radius. Say this nose radius is this is the center and this is the nose radius is let us say r. So, these are the two profiles, okay. Two profiles means for each revolution of the workpiece, tool is moving from this point to this point. By next revolution, it is moving from this point to this point. So, the distance between these 2 points will be equal to f, this is the feed. This is what we are writing, that from here to here valley it will be f by 2, half of this distance, okay. Now, in these two profiles, subsequent two profiles if we take, and then this is the r, okay, this is the r, this is f by 2, okay, because this distance is f and this distance is r minus h, this is the h which is the surface roughness, all right. So, therefore, from OAB triangle we can say that r square is equal to this square plus this square is r minus h square and this square is f square by 4. From here h is very small. So, this is almost equal to 0 we can say. So, from here then we can say that h is given by, this is the surface roughness, is given by f square divided by 8 r. So, you can see now that if we compare this when the tool is rounded off, you will find out that this for a comparable value of the feed, the rounded off tool will give a better surface finish, okay, or less value of the surface roughness. So, therefore, we always say that tool should be rounded off, and tool should be rounded off up to 3 millimeter, because beyond 3 millimeter I will remind you that those components of the tool normal, that is the and the radial direction normal to the tool edge, they will increase, that will detract the tool from the workpiece and there will be self excited vibration. And if it is very small, that is lower than let us say 0.5 or so, then there will be high stress concentration because tool will be sharp. So, therefore, the tool has to be rounded off, and how much it will be rounded off, you can actually take the guidance from this theoretical judgment that this h, that is the surface roughness, will depend on f square divided by 8 r, and r is the nose radius, okay, f is the feed. Okay. In case of milling, it is the feed which is advancement of per tooth, okay, advancement per tooth, and f is the feed per cutting tooth, that means, So, let us take these two subsequent position of the milling cutter when the this is moving, workpiece is moving. Let us say workpiece has the movement or the feed which is Vf, okay, feed velocity. So, if the milling cutter is in one position, but because of this movement given to the workpiece feed movement, here these are the two positions we are considering. Okay. So, this is like this is the profile as the Vf is given to the workpiece while the milling cutter is rotating. So, here also you can see that this is the radius of the milling cutter, that is d by 2, which is here. Okay. Now, from here to here, this is the feed, okay, and this is the feed per advancement of the tooth, because this is for one tooth. This we have discussed for the milling. All right. So, from the OAB triangle, we can say that OB, this is the d by 2, this is the radius, all right, and AB this way, this is f by 2. F is complete distance between these two centers, and this is the half of that. So, this way it is f by 2. So, OA, this is equal to, this is the d by 2, and this distance is the h. This is from peak to valley. From peak to valley, this is actually h, which is A to this point. All right. So, then from this triangle OB square is equal to OA square plus AB square. From here we can put the values which we have seen here, and we can say that h value we can find out as the f square divided by 4d. Okay. So, this is the value that is the surface roughness in case of the milling, and this depends on the f square divided by 4, and the d is the milling diameter of the milling cutter. Now, f we said earlier also, this is the Vf by n into z, you remember we said that. So, f now from here we can find out this is the Vf divided by n into z, these values we can put here. So, f is equal to this. So, therefore, h will be in place of f. If we are putting that Vf by nz, we will find this. All right. So, using this equation, you can also see that for comparable feed in case of let us say turning and milling, the surface finish in milling will be better. Okay. This is simply because the milling will be working with the many teeth, and the single point cutting tool, particularly when the cutting tool is sharp, the surface roughness will be more. Okay. Now, if we see the grinding, for example, okay. Now, here of course, these are the changes that we have shown, that power can be made as this, and there is a small example given that if the Vf is given and the d is given, so how to find out the h. So, of course, you can put in the formula all these values, find out what is the value of the h, and that is what I was telling you, that you can see and compare that this is such a small value in comparison to what you can get in case of turning, for example, okay, with a comparable feed value. Now, let us see what happens in the case of the grinding. In case of grinding, these are the subsequent positions of the grinding wheel, okay, when the feed is given, like in the case of the milling. So, grinding wheel is rotating and the feed is given to the workpiece. So, for each rotation of the grinding wheel, how much the workpiece is moving. So, from here to this is that equivalent. Okay. So, let us say if there are C number of cutting points, okay, let us say, that is earlier we said that C is the grain concentration, capital C is the grain concentration per unit area on the wheel. So, C is the number of cutting points per unit area on the wheel surface, and the average chip has a width B. Okay, let us say average chip width is B. So, the distance between two successive points, that is the grain spacing. So, by two successive points we mean to say that one point here on the grinding wheel and the another point in the grinding wheel. Okay. This will be 1 by BC. Once again I will explain this to you, that if we say that there are C number of grains, okay, per unit area, then from one grain to another grain, that distance will depend on the B, width. So, the width of the chip, okay, that a grain will be producing. So, therefore, 1 by B into that C will be the grain spacing, distance between the grains on the wheel. Okay. So, this distance on the wheel on the workpiece will be Vf divided by Vc times the distance between the two successive points, 1 by Bc on the grinding wheel. Vf by Vc, this is the ratio. Why it is so? Because we have to multiply by the ratio of that feed velocity given to the table and the cutting velocity given to the grinding wheel. So, Vf divided by Vc, if we multiply that into by this 1 by Bc, that will be the equivalent distance on the workpiece, okay, with respect to the distance between two grains on the grinding wheel. So, this is actually the distance, that is the SF, okay, on the workpiece. So, on the workpiece, this distance is equal to Vf divided by Vc into 1 by B and the C. So, B is the maximum width we are saying as a chip, maximum width of the chip, okay, because the two successive grain will produce the maximum chip width, that is what we said. Okay. So, gamma G is B max divided by half of T1 maximum. We already found out this, okay, from this chip, if you remember, and we said that this is the chip, this is the T1 max, okay, and this is the B max. So, the gamma G is B max by half of the T1 max, because it is average T1. So, the B max therefore is equal to half of the T1 max into the gamma G. Okay. Now, the SF that we have written as this, here we are putting the B max value as this and we are getting this. Now, from this triangle, like in case of milling, this square is equal to this square plus this square. Okay. From here we can find out by ignoring the a square which is small, as the SF is equal to 2 root over d into h. D, by the way, is the diameter of the grinding wheel. So, d by 2 is the radius, like in case we have done in the milling. Now, equating both these SF, because SF is this, okay, and here it is. So, we can find out, if we equate that and then put the value of the T1 maximum, which we have earlier found out, that this is the value from the T1 maximum, and from H we are replacing this value to get finally the 225 T1 maximum divided by the D. Okay. And this actually, this D is the depth, all right. So, the H is proportional to T1 maximum square, or this we can say as the T1 square, T1, this is the maximum value, and divided by D. Now, this shows that the chip thickness is the most important variable affecting the surface finish. Okay. Therefore, for better finish, the grinding condition should be such to choose the value of the T1 which will be reduced, because if we can reduce the value of the T1, this is proportional to T1 square. So, H value will be reduced and H is the surface roughness, therefore, the surface finish will be better. So, that is what we said here, that therefore, for better finish the grinding condition should be chosen to reduce the value of the T1. So, here you can see that the surface finish of the grinding is better than in case of the milling, which is better than in case of the turning, particularly for the sharp tool, and for the rounded off tool the surface finish is better than the sharp tool. So, this is what I wanted to tell you in the machining section, and I thank you for your attention. I will discuss the rest of the material in the course of the production technology in the next discussion session. Thank you once again for your attention.